Okay guys, so we're going to spend a few minutes today just talking about differential equations. So I know they sound pretty fancy and difficult, but I promise if you can integrate, you can solve a diff EQ. Okay? So when you deal with a differential equation, you are setting up any sort of derivative and you're setting it equal to an expression. Okay? So differential meaning your derivative, equation meaning equal, and then you're going to have some expression here. So in class today, we looked at the expression negative x over y. So this could be a differential equation. There's a whole bunch of them, right? All of your slope fields, that worksheets that you've done, so x plus y, all that stuff, every slope field represents the solution to a differential equation. So in order to solve a differential equation, there's a few things to keep in mind. First of all, your derivative represents slope, right? That's what it represents, the slope of the tangent line. Now, hopefully you remember from Algebra 1 that slope is not rise over run. Like, that's the value of slope, but that isn't what it means. Slope represents the rate of change of a line, okay? So whenever you deal with differential equations, it's important to identify what the rate of change is. Rate of change of a line. Okay, that's the definition of slope. Slope represents a rate of change. Your derivative, therefore, is a rate of change. Okay, so when we deal with our differential equations, we're dealing with a situation that represents some sort of rate of change. So let's just do one example now involving population growth, right? So everything grows at a rate, our population grows at a rate, therefore we have a rate of change equation. So let's just move this up a little bit. So for this situation, we can call this example 1. Okay, we're going to say that the current population is 1,000 people, okay? So we're dealing with like some small town. Okay, so the current population of whatever small town we pick is 1,000 people, and it is growing at a rate of 5% per year. 5% per year. Okay, and for this problem, my goal, or what I want to do, I don't know, I'm calling it a goal, erase that. Okay, so you want to find the differential equation. Okay, that's the first part. And solve the equation, or solve the differential equation. Solve the differential equation to find the equation that expresses, sorry, I know this problem's long, expresses population as a function of time. Okay, so again, just so we can kind of go over the scenario, we have a current population of 1,000 people, okay? It's growing at 5% per year, and we want to find a differential equation and then solve the differential equation so that we have an equation that expresses population as a function of time. So again, when we deal with any sort of differential equation, we're looking for a rate, which is what they're given to us in this problem. Now, our rate represents population over a year, right? So in this situation, let's consider our population to be P, and our year is our time. So instead of writing dy dx, because we're not dealing with y and x variables, in this case, we want to write dp over dt, because we're representing, this problem represents the change in population over the change in time. Okay, now, our population is growing at a rate of 0.05%, or 5%, which is 0.05. Now, this percentage is dependent on the population of that year, so we need to add in another p there, or variable, and we can say that p is the number of people after the current year. So your population, if we didn't include this p here, this variable, your population would grow by constant value every year. And although it's growing by constant percentage, this percentage is dependent on the current number of people. So like 5% right now of 1,000 would be 50 people. So at the end of this year, we'd have 50 people. But the next year, we'd have to do 5% of 1,050 people. Okay, that's why we need this p there, because your population that you're taking 5% of is continually changing. So this is our differential equation. Okay, we found the differential equation, and now we're going to solve it. So let me just move this up so I can get a little bit more space. Okay, so when you're solving a differential equation, the first thing you want to do is separate the variables. So you want to move all the p's to one side and the t's to the other. Okay, so this is our current equation. dp dt is equal to 0.05 p. So I need to move my p's to one side of my equation and my t's to the other. So let's start by moving dt to this side of my equation, because that's pretty much the easiest step. So I'd multiply both sides of my equation by dt, okay? Remember that d represents a change of the time, so you need the d, this d needs to move with your t, okay? So that's going to leave me with my change of population, so dp is going to equal 0.05 p times dt. Okay, now, I know you, in your head, see this all as a p term, but when we divide by this term, we just want to divide by the p, okay? Leave your coefficient, because that's going to be easier to integrate, okay? We're undoing a variable, so we're going to have to integrate. So leave your coefficient there, because it's easier to integrate without that coefficient, okay? So when I do that, I'm going to get dp over p is going to equal 0.05 dt. Okay, if you really, really need to move that 0.05 over, you can. It just makes your life harder down the line. Okay, now, I have part of a rate equaling the other part of a rate. I want to get rid of dp, I want to get rid of dt, because neither of these are functions of time, right? For a function, I just want p and t by itself, and here I have a relate of my population and a relate of time. So in order to get rid of dp and dt, I'm going to integrate both sides, okay? So that's going to give me the integral of dp over p is going to equal the integral of 0.05 dt. Now, notice this very easily would integrate to the natural log of the absolute value of p, which would equal the integral of this side, which would be 0.05 t plus c, okay? I know you probably want to add in a plus c over here, but you don't need to do that because one constant's enough. It'll make up for the fact that we didn't add one there. Okay, now we're super, super close to being done with this problem because we did the hard part, which was the integral. But if you remember from our directions, we need population as a function of time, right? Where's my highlighter? Population as a function of time, okay? So if population's a function of time, we can't have our population be, whoa, sorry, that was weird. We can't have our population be dependent on a natural log, because then our population's a function of our natural log, which is a function of time, which doesn't make sense. So we have to solve this equation for p. So from Algebra 2, we are going to raise this entire equation to the power of e, which is going to give me e to the natural log of the absolute value of p, which is going to equal e to 0.05 t plus c. Okay, now we're going to keep going because we're almost done. Hopefully you remember from Algebra 1 that ln raised, or e raised to an ln cancel each other out. So on this side, we are left with the absolute value of p. And on this side, if we use our exponent rules, we're going to get e to the 0.05 t times e to the c. Okay, we're almost done. I promise you. Now, e to the c is going to be a constant. We don't know really what that constant is yet, but instead of writing e to the c, we can just change this to be one big constant. So instead of calling it c, we can just call it c1. When we do that, that's going to account for the fact that we have this absolute value here. Okay? So that's going to give me p is going to equal c1 times e to the 0.05t. And if you even want to, you could say c1 is equal, this is a comma, I don't know what that looks like. c1 is equal to e to the c. Okay, now we are super close to being done, I promise you. The last step is we need to solve for this c1 value. So if you remember, at the very beginning, I said to you, the current population is growing at is 1,000. Okay? So our current population is 1,000, and currently our time we're at year 0 because we're starting to grow now. Okay? So this information here, the fact that we're at population of 1,000 and we're at year 0 because we're starting now, we can plug into this equation to solve for c. So our current population is 1,000. So 1,000 is going to equal c1 times e to the 0.05 times 0, which is going to give me 1,000 is equal to c1. Okay? So this becomes 0, so this term becomes e to the 0 power, which is just 1. So now, last step, I'm not lying, it really is the last step. We got to plug in c1 into our equation. So our population is going to equal 1,000 e to the 0.05 t. And that is our population as a function of time.